All right, here we go. Hey, everyone. Welcome back to our CRAM sessions for AP Stats. We've been bumped back an hour, back to 9 o'clock p.m. Eastern Time, and this is where we're going to be living for the foreseeable future. We had some conflicts last week with timing, and so we wanted to make sure that we could get those all sorted. So thank you guys for your flexibility and for your understanding. And this is where we'll be, like I said, for the next several weeks on Mondays. So big picture-wise, we did get some clarity last week in terms of what the AP exam is going to look like. Remember, it's still the first 7 units and only the first 7 units. So when you're looking at this table, units 8 and 9 are not going to be covered on the AP exam. So we've got units 1 and 2 are our data analysis. We've got unit 3 collecting data, and then probability rules in units 4 and 5. And then the last half of the course is all inference, but we're going to be sticking to unit 6 and 7. So just z-test, t-test, confidence intervals for proportions and means. But what we do know now is that the exam itself is going to be 45 minutes. And that includes like a 5-minute upload period for yourself. They're suggesting that there are going to be 2 free response problems. They're both going to contain multiple topics. The first one should last about 25 minutes and the second one should last about 15 minutes. And so I can see it being the kind of thing where there's, you know, a prompt with a couple of graphs at the top and you've got to describe them. And then they ask you to maybe do some predictions and inference down the line. They are very explicit that each question will contain at least 2 of these big 4 topics. And so it does change how we look at some previous examples to try to predict what's coming next. But it means that everything's fair game. And so in the grand scheme of things, you know, we're going to stick to our flow and we're going to keep practicing free response style questions for each of these units. And so last week, if you were with us, we did 1 variable data. We looked at mostly histograms and reminded ourselves of how to describe or compare distributions. I saw some folks did the problem on our community page. Thank you for those of you that did that. And today we're going to get into 2 variable data. And so as I see people trickling in here, we're going to start off for maybe about 10 minutes or so talking about what categorical variables can look like when we're comparing 2 groups at once. And that's going to be specifically with two-way tables and segmented bar graphs. And we'll talk about how to show if there is or is not association between those graphs or if there's independence between those 2 variables, excuse me. And then quantitative variables are specifically about scatterplots. That's the only type of graph that we'll see for 2 quantitative variables. And then the bulk of our work tonight, my goal is to spend at least a half hour or so working with linear regression. That is a big part of Unit 2. And so that is using regression lines. That is talking about slope and intercept. That is talking about residuals. And that is reading the little computer outputs that sometimes come from, you know, inputting a bunch of data into either a calculator or a computer program and getting some results there. So with that in mind, okay, that's our big picture for tonight. It's been, 3 or 4 minutes. We see, I think about 11 of you guys here. Welcome. Good to see everyone again. And let's get into it, shall we? So categorical data, okay, if we are going to have 2 variables being measured about individuals, like, for example, an opinion question, yes or no, and then break it down by gender or by age or something that could be split into categories. Really, the only types of graphs we'll see for that are, one's not even a graph at all, two-way tables, kind of like this. So this is a scenario from 2011's exam. The scenario was about 500 voters in a town, and they broke down the gender of each voter and what party each voter was registered for in an upcoming election. You see party W, party X, party Y. And then they also turned that table into this thing called a segmented bar graph and asked if there was any association that appears between party membership and the gender of the person. And so really the only thing that we can do to compare the 2 different groups or compare the parties amongst the different genders is to talk about proportions. And so based on this graph, I would go ahead and if I was asked to describe association, I would say something like, well, it appears that men are more likely than women to join party X, as amongst men, there is a greater proportion in party X than there are women, but women are more likely to join parties W and Y as compared to men. because, as you can see in the segmented bar graph, the proportions are bigger. That doesn't mean there are literally more women or more men in either of those two groups. It just means that the proportions are bigger. But the other thing that you could be asked to do is describe if something is independent when it comes to two categorical variables. And we'll get into this more when we review probability rules. This is something that comes up with probability sometimes. But that happens if the conditional frequency, meaning the percentage within each category, is the same as the overall percentage of the entire category. So we would like cover up the inside of this table and just ask ourselves, okay, if the party alignment is independent of gender, that would mean for each gender, the percentage of people in each party is the same. Or for each party, the percentage of each gender in the party is the same. Kind of break it down like there's 300 women and 200 men. And so out of the 500 total people, 244 said party X. Okay, 244 out of 500 is about half. So that would mean if the gender and party variables are independent of each other, then about half of the women would be in party X and about half of the men would be in party X, because about half of the total people are in party X. Now, that didn't happen in the actual real data. You can see that there are way more than half the men in party X, 124 out of 200, and there are way less than half the women in party X, 120 out of 300. So this is not independent. But if it was independent, then those segmented bar graphs would line up perfectly based on the overall proportion. Honestly, this really isn't a thing that's asked about a ton. As you can see, in the last 10 years, it's only come up in 2011 and 2014. So if I'm a betting man, I'm not assuming that that's what's coming up this year, especially with the reduced question load. But it is fair game, so you never know. So let's look at that example from 2014. And the scenario involved asking a group of students whether or not they participate in activities at their school, extracurricular activities, and if so, how many they do. And you can see a graph of the data shown here. So let's write a few sentences summarizing what the graph reveals about the association between residential status, on versus off campus, and the level of participation in extracurricular activities, how many you do, if any, amongst the students in the sample. So you can see we've got none, 1, and 2 or more as the level of participation categories. You've got on and off campus as the residential status. So let's spend a couple of minutes here and then we'll move on to quantitative variables. Write a sentence or two. You don't have to try to craft a full answer here, but I would love to see some people throwing some answers into the chat about what you see based on this graph of data, summarizing the association between residential status and level of participation. Give it another 30 seconds or so before I comment on any of the responses that have come in so far. Yeah, I was going to just ask about that. I was like, I think, especially from context, I saw the whereas. Yeah, I mean, Anna, your sentence makes sense. Students on campus participate in a larger proportion of extracurricular activities than do off campus. Kate, you said your residential status does not necessarily affect participation. That might be true, but just based on the graph we're seeing, are there any trends? So you might be right that there really isn't an overall picture here, but are there trends that we're seeing in the graph? And Allison notices the trend that students who participate in no activities are more likely to live on campus, whereas students who participate in one extracurricular activity are more likely to live on campus. So you're sorry, Allison said off campus for the no activities. And Israel says on-campus students have less people doing activities and more people no activities and more people doing one activity. 2 plus is about equal. Okay, the one thing we want to be careful with when we are describing associations of categorical variables is the only thing we can compare here is not raw numbers. We don't actually have the raw numbers to work with. We have to be comparing the percentage or proportion. So your response needs to include the phrase proportion or percentage, because that's really the only statistic we can calculate about categorical variables. So if I take Israel's response and add proportion of people doing one activity, proportion of people doing 2 plus activities, proportion of people doing no activities, then that's going to be a fully captured answer. But as it stands, referring to try to refer to the number of people isn't going to cut it. And Allison, when you say more likely, that is referring to proportion without explicitly doing it. So you want to make sure that you explicitly compare proportions. Kind of like when you're comparing graphs of quantitative data and you have to explicitly state like the median over here is greater than the median over here. The thing to cite for categorical variables is the proportion over here is bigger or smaller or less or equal to the proportion or percentage over there. So make sure you're really clear with that. But ultimately, as long as you've compared at least 2 of the groups for on versus off campus, you're getting full credit here and referring to proportions or percentage. And that, should you explicitly say the word proportion in your answers? Either that or percentage, yes. You can say students who live on campus are more likely to participate in one activity than students who live off campus because the proportion of students is higher or because the percentage is higher. That's your evidence for the reason that they are more likely to participate, because you're comparing those 2 percentages. Kind of like if this was a quantitative graph and it was like how long it takes to get to class or something, you might say, well, the students who live off campus take longer because the median length of time is higher, or like you'd have to cite some sign of statistic. So the statistic here is proportion. And so yes, you should do that. To be fair though, doesn't come up a whole lot, but I definitely did want to touch that, like I said, for about 10 minutes and it's been 11. So let's keep it moving. The thing that comes up more often when we're measuring 2 variables about individuals at the same time is 2 quantitative variables. And that will be graphed as a scatter plot. So if you're measuring 2 quantitative variables about an individual at the same time, that is time for scatter plot. So you see this scatter plot has measured the height of people as well as the arm span of people. And scatter plots show up almost every year. So over the last 10 years, it is a scatter plot. At least one scatter plot has appeared on the free response section 6 of the 10 years. And one of those years, there was a description of a scatter plot, but no actual picture. So it is a pretty common question stem. And remember that when you're looking at scatter plots, you've got an explanatory variable. Explanatory variable goes on the x-axis. And that's the one that's explaining the change in something else. And in this case, height is my explanatory variable. And you've got a response variable that is on the y-axis. In this case, arm span. And that is the result of something else. And you should be able to predict stuff for the response variable using the explanatory variable. So if I tell you how tall someone is, based on this graph, you should be able to predict how long their arms are going to be. And if there's an experiment going on, it'll be super clear where to graph stuff. And the thing that you're often asked to do when you're looking at a scatter plot here is describe it. So how would, you can go ahead and put this in the chat, how would you describe the association between height and arm span for the students in this sample as shown by this scatter plot? So I see 1, 2, 3, 4, 5, 6. I see 12 dots. There's 12 students. They measured their heights and arm span. For those 12 students, how would you guys describe the association that you see? So when it came to the Categorical variables, you were describing association based on percentages comparison. We're going to do it very different. Okay, I see positive, positive, positive. All true. Any other descriptions you can give besides positive correlation here? Because I agree with all of you. Oh, Olivia's adding some more words here. Somewhat strong. No, strong. It was, it's in caps. That's important to really, really say what you mean. Okay. Yep. As you get taller, the more likely you are to have longer arms. As height increases, arm length increases. All true. And those are all really great ways of saying positive. Now we're getting somewhere. Hannah's now asking, oh, wait, is this linear? Turns out if you're describing associations on a scatter plot, the AP exam is looking for you to do 3 different things with your description. So you guys all gave me a direction. You gave me that it was positive. But Hannah just got to the idea of form. So when you're describing, okay, a positive association just means as one variable increases, so does the other in general. But the form is going to tell us, well, how does this increase? Does it increase steadily with a linear association? Or do we increase in, like you see with COVID-19 cases, exponentially? Or do you increase logarithmically? Or do you increase really just non-linearly? So AP Stats isn't concerned with all the different types of functions you might study if you're in calculus. Don't worry about that. Linear, non-linear. And then someone also mentioned strong. Okay, we have to mention the strength of the association. So there might be a strong association. There might be a moderate association. There might be a weak association. And then the worst case scenario is that there's just no association. The dots are all over the place. There's no clear pattern here. So for this scenario, a sample response would be there is a positive, linear, and you can say moderately or just say strong association between height and arm span for the students in the sample. Moderate, that's the word you're looking for. Yeah, you could say moderate or moderately strong. Yep, I would go, me personally, I would have called this moderately strong. And to remind us of like, what the heck, what do all these words mean? Okay, you guys already got positive and negative. The positive and negative is, hey, as one variable goes up, what does the other one do? So the technical definition is look for above average values of X. If the Y values also tend to be above average, that's a positive association. And if the Y values tend to be below average when X is above average, that is a negative association. But in this case, it's taller people tend to have longer arms. That's a description of a positive association. Linear versus nonlinear, you're describing what do the dots look like on the graph. Do they look like they're forming a straight line or a relatively straight line? Then you've got a linear association. And if they look like they'd be better fit by a curve, then you're going to say it's nonlinear association. So it might look like this. They might look like that. Anything that's not clearly a straight line, you can call nonlinear. And then strong, moderate, weak has to do with once you decide the form of the association, do the dots look like they would be very close to whatever line or curve you're applying to that graph? You've got a strong association. If they're kind of somewhat close, you've got a moderate to, you kind of in the middle. And then if the dots are very scattered far away from the line, you might have a weak association. When we get into residuals later, we'll circle back around to this point because these words have to do with the average size of residuals. So if the residuals are typically very small, that means the predictions are very close to the real things and you've got a strong association. And if residuals are typically pretty big, then you've got lots of scatter there and you don't have as strong of an association, a little more weak. So with that in mind, let's practice a little bit putting some of this in context. Marine biologists studying a group of wild salmon collected data on the weight of female salmon prior to mating season. That's going to go on the x-axis. And the number of eggs those salmon laid during mating season, going to go on the y. Scatter plot of the data revealed a positive, linear, and strong relationship. Kate asked, will they ever give us a graph with no correlation? Probably not, especially not in a year where there's only 2 questions. I have not seen it, at least in the last 10 years, on the free response section, not have a graph with no association. So for this scenario with the salmon that's described above, not drawing a picture for you, let's just write a sentence each for what we mean by positive, linear, and strong. What would we mean by positive, linear, and strong? Let's start with positive. Let's write a sentence for positive. What do we mean by positive? In the year that there was a question similar to this, they were pretty clear in the rubric that you could draw a picture, but the picture alone could not answer this question. You had to write something that goes with it. As the weight of the salmon increased, their eggs number increased. Weight of the salmon prior to mating season increases. Number of eggs during mating season increases. If the salmon is heavier, there will be more eggs. Yeah. I think you guys are all getting there. One thing we want to be careful with when we're talking about associations is these are tendencies and not guarantees. So it's good to say things like tend to, are predicted to, should, things like that. Because there's no guarantee that just because you get heavier, you will lay more. The relationship shows that happens. You're not going to get deducted for saying that. But yeah, heavier salmon tend to lay more eggs. What about linear? What do we mean by linear? This is the part where a bunch of my students just kind of like draw a picture and like, I mean that, but in words, what does it mean to be linear in this case? So heavier salmon do tend to lay more eggs, but what about linear? Okay, Anna says increasing at a constant rate. Josie moves in a constant trend. Olivia goes straight up or down. Same approximate correlation for each point. Weight increases. Eggs laid also increase at a constant rate. So, all right. I like Israel's response because it ties together both the first and second points here. So like positive and linear in the same sentence. Constant is a nice word. Olivia, I'd be careful saying it goes straight up or down. That almost implies like there's something like this. Like you might be trying to say like the dots move in a straight pattern or a straight line, and that would be okay. But saying just straight up and down is fine. So I went at it from a like, what is the graph going to look like? A line is an appropriate model of the relationship between salmon weight and number of eggs. Yep, that'll work too. The data appear to form a straight line on the scatter plot is the kind of thing that will be accepted. In the year that this was done, here are some sentences that were not good. The points all line up. No good. You can draw a straight line through the points. No good. Because a straight line doesn't just like a straight line might be flat across. And if you have a flat straight line across, there's actually no association. The line has to be clearly increasing. So referencing the constant rate of change, I think, is a good technique there. All right, so we've done positive, we've done linear. Let's do one more. What about strong? What do we mean that there is a strong relationship between the weight and the number of eggs being laid? Line of best fit would look nice. Alejandro, that is a true sentence. A line of best fit would look nice here. We are going to have to use a little bit more precise language when it comes to the AP exam. Olivia, high R value is probably true, but that is not enough to state that this is a strong association. Kung Flu Panda. These names are creative. A line is a good model and most points fit close to the predicted values. Yeah, that's going to do it. The displacement of the predicted values and the observed values would be relatively close. Hannah, that would probably do it. So strong. The number of actual eggs laid tend to be close to the predicted number of eggs laid. Coronavirus guy. You're giving me a new name each week. Love it. Olivia, Alejandro, we're going to come back to this in a few minutes here and like kind of clean up those descriptions. So positive is usually the one. It's like positive, negative are really easy to describe. Linear is fairly straightforward. Then that strong, weak, it's a little bit trickier until we get to residuals. So someone just mentioned R. It's a good way to transition. Remember, R is that number. It's called correlation. That describes linear association. So this number R is quite literally a single value that can capture the direction and strength of the linear association that you see. So remember, R is between -1 and 1. -1 would mean you have a perfectly linear negative relationship, straight decreasing line. 0 would mean there is no linear relationship. We're going to see a bunch of zeros in a few seconds here. Doesn't necessarily mean that there is no relationship, just no linear relationship. And +1 would be a perfect positive straight line. This graph has a correlation of about 0.9. And R, in terms of like how to calculate it, it's the kind of thing that very rarely will come up in multiple choice settings. It has to do with like dividing the standard deviation of the two separate quantitative variables you measured by another measurement. And it's just honestly not something that we need to worry about. But here are some pictures of R. So does correlation only refer to linear models and association refers to all models? Yeah, sometimes they're used interchangeably. Correlation coefficient, that singular phrase, is specifically R, which is just for linear. But the phrase, oh, there is a correlation between X and Y, could potentially apply to different types. And so we use the more generic term association for that. Correlation coefficient is the name of R. And here are a bunch of pictures of R. So you can see the top row has some generic looking scatter plots that are fairly linear in nature. You notice like when we're getting into the middle there, that 0.4, -0.4, there's pretty weak associations there. You can see a positive trend and a negative trend, but pretty spread out. The second line has all perfect associations. So the thing to notice from that is it does not matter what the slope is, as long as there is a slope and you have a perfect straight line. Okay. But if you have a perfect horizontal line, there's no association. And that's because the slope would be 0. And that would basically be saying no matter what the explanatory variable is, the response variable is the same no matter what. So there's no association. There's no increase. There's no decrease. And then the bottom row has all the fun patterns that are nice patterns, but not linear patterns. And there's no clear trend. What point would you say is a good R value? Typically strong associations. We see R is like 0.9 or above. 0.8 something could work too. And anything that's lower than like 0.3-ish is kind of like, there's not really much of an association there. In small data sets though, like a single data point can have a really big deal and can like really mess with your value of R. And we'll see a couple of examples of that coming up pretty soon. I do want to get in though, as promised. The last half hour, I really want to spend some time on linear regression. So we've talked about how to describe association with either categorical variables or quantitative variables. So association for categorical is comparing the proportions in separate groups for the two separate variables. And association for quantitative variables is talking about, I call it in my class FDS, form, direction, strength. And then sometimes my students say some not nice words instead of FDS, but I think it's funny. Form, direction, strength, describing the scatter plot that you see. But most of the stuff that is asked in the free response section for this particular unit is about linear regression, is about actually using that line that we can draw through the dots to make predictions. Okay, so linear least squared regression line, you guys know it from Algebra 1 or Algebra 2 as a line of best fit. And it's the thing that's quantifying the linear relationship that you see. So the line itself is used to predict values of the response variable based on the explanatory. So like if you had to predict the arm span of a new student who was not in this data set, who was 65 inches tall, well, you could go to 65 on the x-axis. You could draw a straight line up to where the line is and look over to the y-axis, and that would be your prediction. But what you would probably want to do is just use the equation. And so you might recognize this equation from first semester. Remember the different parts of it. You've got x is the explanatory variable, not u. X is the explanatory variable. Y hat, that is a little hat over the y, is a predicted value of the response variable. It's kind of like how p hat is for a sample, but p is for the entire population. Oh, because he's fancy. That's very cute. It's because I'm going to steal that. It's because he's fancy. You're right. It's because it's just a prediction. We're not entirely sure if it's going to be exactly right. So the little hat signifies that it's a prediction. The actual y coordinates are the dots themselves. Yeah, everyone likes y equals mx plus b, but the different form reminds us that this is for predictions. And so it's not always going to work out as nicely as that y equals mx plus b stuff. The A coming first represents the intercept. We're going to learn to interpret this in a couple of minutes here, but it's the predicted value of the response when the explanatory is a value of 0. And the slope is the average predicted change in the response per 1 unit increase in the explanatory. Yep. The word predicted is like the biggest thing that messes with people in this section. Is like you're so used to writing about relationships and doing it like this increases, therefore this does. We have to make it clear that it's a prediction. Okay, so if you're given an equation for a least squared regression line like, oh, this one, okay, they're actually really easy to use. If you had to predict the arm span for a student who is 61 inches tall, it would take us about, 30 seconds or so. Like, you don't have to actually do it, but what would you do to make this prediction? Like, just type a 1-sentence answer. What would you do to make this prediction? Yeah, plug it into X. Just pop it in. In 2015, this was actually a question. It was, hey, they had given 2 lines, and you had to pick that this line was the one that was the best fit, and you had to just plug in the given number. But the thing that got a lot of people was you had to give units with your answer. And so a bunch of my students got partial credit because they just wrote the number and didn't write inches, which is how they were measuring arm span. So context for everything, put units if they're giving you units to use. But yeah, just pop in whatever number is. And so our predicted arm span for another person who is 61 inches tall is about 62.37 inches. Sometimes, though, you'll be asked to make predictions for people who are not in the original data set and who have heights or who have x values that are outside the range of the current scatter plot. And that is called extrapolation. And that could be dangerous. I mean, it's right there in the word, extrapolation. You're doing extra. You might not be able to make that prediction. Okay. And so I've seen sometimes where you're asked to make a prediction for an individual that is outside the current range, and you can make that prediction, but you need to make a statement about how this is extrapolation, so this is an unreliable prediction, or this may not be true because, and then you come up with some possible confounding variable that might mess it up, or explain that the trend might not last. So like in this case, I've got a bunch of, height. These heights are all between 5 and 6 feet. If I tried to predict the arm span of a child who is only 34 inches tall, I don't know how the proportions of kids' bodies are going to be the same as the proportions of, teenage bodies of people in this data set. So it might not work. It might be okay to make this prediction. It might not. And you have to make a statement that predictions based on extrapolation are unreliable, potentially dangerous, so to speak. And I've seen that be a thing before. So just be aware, extrapolation, you do an extra, don't do it. Okay. What you are often asked to do for least squared regression lines is interpret slope and intercept. Someone mentioned this before. Okay. So this is a scenario that was on the AP exam in 2018. the scenario was a store manager was running a little observational study to see how the number of people in line affected the checkout time, like the wait time before someone got a chance to check out. So you can see they got anywhere from 0 to 6 people in front of the customer, and then they put a stopwatch on these 11 different customers and timed how long their transaction took. And the slope of this line happened to be 174.4. And so that slope represented the average predicted change in Y per 1 unit increase in the explanatory variable. So in this setting, what sentence would you write for the slope? Like, what would you say the number 174.4 represents in this case? And if you're looking to just plug and chug into a little formula template, I've got one for you, but you can also put the sentence into your own words, and we'll talk about it in a little bit. So go ahead and put in the chat, well, how would you describe what this number 174.4 represents in the context of this scenario? Ooh, neck's a little sore. Thank you for that addition. Allison also tends to increase. Okay, that should be good. We have to make it clear that it's a prediction. So I like that I see the word predicted in Kung Flu's answer. I see the word predicted in Israel's answer. Yeah, so I would say as the number of customers in line, yeah, tends to increase. That should, I got to double check that. Yeah, Kate, that's a really good question. So it actually made me think of how questions like this are actually a little bit less likely this year, especially in the linear regression unit. Interpreting intercept, slope, R squared, and S, like people use templates. And that's totally fine because most years on the AP exam, you're not doing an open notes test. And so it really is a test of like, do you understand that you have to say predicted, that you remember that this is, you know, about this, not that. So even though I think it's a thing that's worth reviewing, I don't know that you're necessarily going to be explicitly asked just for the slope. What I could see happening is they sneak this language into a question. And so you have to recognize that, oh, they're talking about the slope. So maybe they ask you to like predict how much longer it will take for this if they add, you know, 5 more customers in line. Is like, oh, that's the slope sentence. I should multiply the slope by 5 or something like that. So it's tough to say, but I mean, they still could potentially ask us to just interpret whatever. And then that's where like, I'm definitely telling my students and telling y'all to come up with some kind of cheat sheet where you have, you know, these sentence templates ready to go so that if it does come up, reference it and you're good to go. So with that in mind, let's keep doing some sentence templates. How the intercept is the predicted value of Y when X is 0. So in this case, I'm not even going to put the template up. I'll let you guys try to write a sentence. Yep. So how would you interpret the number 72.95 for this scenario? Approximate wait time. Hannah, that should work. Let me see. By the way, the year this was the graph on the AP exam, they asked for the intercept and not the slope. Yep. The number is statistically meaningless. Ooh, interesting. Kung Fu, why do you say it's statistically meaningless? Time will already be at. All right. Israel, be careful. The time is not guaranteed to be at. Okay, because you can't have 0 customers. Okay. That is, I mean, a fair statement in general. I can't have 0 customers, but in this context, and I didn't give the full prompt above it, the customers in line was referring to how many people are in front of you. So you can have 0 people in front of you if you're the first person to enter the line. So it was actually a meaningful interpretation in this scenario. There are plenty of scenarios when it's not a meaningful interpretation. Let me pull this up. The actual rubric was you had to identify 72.95, which you all did, communicate the y-intercept has both time and 0 customers, and indicate that the value is a prediction using language such as predicted, estimated, approximate, or average. So I think you guys all did that. So shout out to you guys. And so, yeah, I would just say when explanatory is 0, the response is predicted to be whatever. And you guys did that here. So as someone mentioned, though, sometimes the intercept is meaningless in context. So this is a scenario, this is a scatter plot that shows the length of time it takes someone to sprint down a runway and how far they jump after running down that runway. And, so the slope here is negative because the longer it takes you to run, that means you're slower. And the slower you are, usually the less far you'll jump. I know as a track and field coach, for long jumpers, we're always looking for our fastest sprinters to transition over and try the jumps because they build up the most speed and power and they can jump the farthest. But in this case, if I tried to interpret the number 414, I would say a person who sprints for 0 seconds is predicted to jump 414 inches, and that is just totally meaningless. You can't sprint for 0 seconds. It has to take you some time to run down this runway, and that was extrapolation in this case. So you will very likely only be asked to interpret an intercept if it makes sense in context, and if it doesn't, they won't ask you to interpret it. They'll ask you to talk about, hey, did the intercept make sense in this context? If so, say something about it. And if it doesn't, explain why. And the reasoning will either be, this is extrapolation, or it doesn't make sense to have 0 seconds of running time, or 0 people, showing up for something, or whatever the scenario is. So I think we should be okay there. Let's do mental stock. We've done slope, we've done intercept. I'm going to skip the practice problem for slope and intercept because, I'm seeing in the chat already, I think we're doing really good. And I want to be respectful of time, and I want to make sure we get some practice in on residuals. So I'm going to skip ahead to that. Let's remind ourselves of what a residual is. Flaw in the formula if the intersect is meaningless. Israel, there is not necessarily a flaw in the formula. The formula is made, I'll go back to this line. The formula is made to fit the data that is there. So this particular equation, y equals 414.79 minus 45.74x, that particular equation does the best job of going through these particular data points. Yeah. Kung Fu is making a good point here. It's not meaningless in math. It's just in the real life context of the scenario, it wouldn't make sense to talk about an intercept. And if you actually look at this scatter plot carefully, it's kind of drawn. It's a little weird. Like it looks like the y-axis is right there, but it really wouldn't be. Like that time on the left is 5.0. So the y-axis wouldn't be right there. The y-axis would be way over to the left, and that line would have kept going up. So it fit this data really well, but it wouldn't fit data that isn't there, if that makes sense. I hope that answered that question. Before I hop into this, if you guys could type a sentence or two, what do you remember about residuals, if anything? So what is a residual in the context of linear regression? Cool. Love it. Kind of like how far off we were. Observe minus expected. Hannah, someone did chi-squared recently, or maybe you took a bio. Yep, observed and expected estimate of how much the true value varies from the predicted value. Allison, it's a residual itself is not an estimate. A residual itself will be that amount, but there is a statistic that will estimate the average residual for us. We'll get to that in a few minutes. But you're right. A residual is the difference between an actual observed value minus the predicted value. So it is y minus y hat. Actual minus predicted, or in the language of chi-squared tests, observed minus expected. Exactly, observed minus expected. Observed y minus expected y. When we talk about the strength of a linear association, the lower the average residual is, the stronger the linear association is. And if you have a particularly high residual, that can be a way to identify an outlier in a data set. So on that graph with the customers in line, there was a clear outlier of that dot way at the bottom with 3 customers in line, but the super short time. That has a really big negative residual, and that could be justification for why that particular dot is an outlier. So you guys got it. He cut the line, maybe, or maybe it was the express lane, you know, who knows, who knows. But in context, okay, so you see a circled athlete on here. This person, the actual X was 5.7, the actual Y was 131. But if we look up at the line, the Y hat is about 154. So that person's residual is negative 23. That person actually jumped about 23 inches less than predicted. And so if you're interpreting a residual, you just need to say, oh, the actual value of whatever the response is this many things either above or below the prediction. So actual minus predicted. If you have a positive residual, that means the dot is above the line and you therefore underestimated the truth. This messes people up sometimes. Positive residual means we had an underestimate because we were actually above the line. Okay, if you're actually above the line, that means the line is too low. We underestimated what the actual result was going to be. The opposite is true for a negative residual. Negative residual means we overestimated with our prediction because the dot is below the line. And if you have a residual of 0 or a residual really close to 0, that means the actual value was really close to what was predicted. The prediction is accurate. If there is no residual there, that means you're on the line. So in this case, point B goes with the first bullet point. Point A goes with the second bullet point. And point C is really close to being that third bullet point. Okay, so whoever athlete B is should be excited. They jumped farther than we thought they would. Whoever athlete A is should be disappointed. They jumped shorter than we thought they would. And athlete C pretty much nailed exactly what they were supposed to be able to do based on this data set. So let's do athlete A. Oh no, I'm not a jumper. I'm a long distance runner. So any of this sprint stuff, that wasn't me. And I'm representing my team. I've got my school's track shirt on right now because I am our school's coach. I'm definitely a theater kid. So, all right, Hannah, that's yeah. That's not to say theater kids can't be athletic. You know, you guys do a lot of stuff. It's all good. Let's do a practice scenario. Same situation with the salmon from before, the salmon and the eggs. Here's the equation of the regression line. So let's do a scenario here. Let us calculate and interpret the residual for a salmon weighing 28 pounds that laid 337 eggs. I love the banter in the chat. You guys are fun. So you guys told me a residual is y minus y hat. Good times. Good times. So you guys told me the residual is y minus y hat. So let's calculate that residual and interpret the result that you get. Ooh, martial arts. That's pretty cool, actually. I never got one of my cousins got her I think she got up to black belt. I know she got brown belt. I don't remember if she got black belt, but she was in it for a while. See? Fair enough. Fair enough. I played Little League. I think I got some Little League trophies back up there on that cabinet somewhere. Back in like 5th grade, and then kids learned how to throw curveballs, and I was toast. Couldn't do it. If it wasn't going straight, I wasn't hitting it. So started running, and I haven't stopped since. But you guys should be cranking out some calculations here, hopefully. I've got my handy dandy calculator, and I will start taking answers here in about a minute. About a minute. You know, I never noticed that. But damn, if you're not right, we do. That is pretty much part of the playbook. I wish I could tell you that there was, some conference we all went to that they told us that, but I mean, it is helpful. I am independently told every year that I apparently look like the dude from Blue's Clues, which I disagree with. But I guess if I'm wearing a striped polo, which I sometimes am, you can see it. So I have my handy dandy calculator, just like my handy dandy notebook. None of you are using this handy dandy calculator right now. I'm gonna need someone to put an answer in here. Yeah, there we go. Thank you, Olivia. I was gonna cut it off in about 30 seconds anyway, because we only got about 10 minutes left here, and I want to make sure I'm respectful of time. So it looks like Anna got to 10.86. So let's break it down. We have the actual Y. The salmon literally did lay 337 eggs. The Y hat, you plug in the X. You plug in the X and get 28 pounds for X. You get a prediction of 326. Okay, so we made an underestimate. Israel, be careful with your subtraction order. We should be doing Y minus Y hat. So 337 minus 326.14 is 10.86. 10.86. And so in context, we would have to identify the specific salmon. So that salmon that weighs 28 pounds actually laid 10.86, or about 11 eggs more than predicted by the least squared regression line. Yep. All right. So we're good here. Do we do our calculations? Honestly, calculating residuals is about as intense as calculations get outside of the probability unit. AP Stats is much more about writing and communicating than it is about doing math. What I have seen is sometimes, and I'm going to just briefly touch on this. Oh, you guys are killing me. Oh, boy. Is what I have seen is sometimes instead of giving you the Y and making you find the residual, they will give you the residual and make you find the Y. So just for the sake of time, in this case, you still need to find the prediction. So we still need to find the predicted number of eggs. In this case, it would be 144.14. And then we can use the residual that is given to us. I'm going to just ignore this chat for a second. We can use the residual that is given to us. It's negative, meaning we actually laid fewer eggs than predicted. So we could subtract that 21.14. Some people also set up an algebraic equation and say, oh, negative 21.14 equals Y minus Y hat. And I get the Y hat, solve for Y, and I'm good. Nah, you guys aren't going to break me. I've definitely heard worse. Although, don't take that as a challenge. I now immediately regret that decision because I feel like you guys are going to now start saying whatever. Also, it's like late at night. This later for me. I'm an old person. 10 at night is getting a little late. So just like check for understanding. Scale of 1 to 5. We good on residuals. I don't want to. Yeah, good. Okay, cool. I don't want to underestimate the amount of time we need here. That's not a very good one. Scale 1 to 5, yes. Fabulous. I am so glad you're feeling good. Okay. The other thing, sometimes we do see residual plots. I could see this being a thing that shows up this year because it's not like super straightforward. Instead of showing us the regular scatter plot, they could show us the residual plot, which still has the x-axis, same x-axis, but then it will show basically just, the actual residuals flattened out. It takes the regression line and flattens it out onto the graph. So you see at 0, dots on the line are still have small residuals. Dots above the line have big residuals, positive. Dots below the line have big negative residuals. And yep, on our regression line, whatever, you might see a residual plot. If there is randomness, if there's scatter on the residual plot, that's a good sign. You do not want to see clear associations or clear patterns on a residual plot. If you see clear patterns on a residual plot, that means there must have been some kind of curvature in the original graph, and that's no bueno. So you do not want to see like a nice linear line or a nice parabola or any kind of curvature in the residual plot. Means the linear regression line was not a good fit and we should do something else. And last skill for the evening here, you remember these guys? Seeing this with the S and the R squared and the predictor and not puns. Remember these computer things? Yeah. Okay, well, there's like a specific way to always read these. They always give us the same style of regression of a computer output on the AP exam. They make it a consistent format. Okay, bottom, weird circle thingy. Bottom left, okay, bottom left of the, not the S, but the bottom left of the main output there, that is always the explanatory variable. If they don't show you a graph, that's what you're looking at, okay? Explanatory variable is there. The response usually isn't there. And then whatever's directly next to that is your slope. Whatever's directly next to the explanatory variable is the slope, because the number attached to x is the slope. Mind-blowing, I know. And then the number next to constant is the intercept. All that stuff about standard error, the t-test statistic, the p-value, it would have been relevant to us if Unit 9 had been on the AP exam, so we can just completely and totally ignore it. They're not going to ask us about it because we're not doing inference for slopes. So the only thing that they could ask us about if they do show us one of these this year is the intercept, the slope, the S, and the R squared. And S and R squared are templates just like the slope and intercept. So like we talked before, I wouldn't be super sure that they're going to, that's what they're going to pull, especially with limited questions. But they might, so you never know. S is the standard deviation of residuals. So it's basically going to capture how far off a typical prediction is. So when S is low, that means that the average distance from the line is low. And when S is big, then you have a pretty big distance from the line. And you would say, if you're asked for S, okay, you'll want to, come back and grab this template at a later time. When using the least squared regression line to predict the response from the explanatory, we're typically off by about whatever they're saying there, because that S is a typical residual. You could think of it as an average residual. It's the standard deviation of residuals, but it's an average distance off from what your prediction is, what we actually are. In this case, the value of S is pretty heavily impacted by that one outlier. If we took that one outlier out, the value of S would go way down, because we're not typically off by 200 seconds. We're off on average by 200 seconds because of that one person who maybe cheated the line. Who knows? Okay, but if you were to write a sentence about it, I would say, when using the least squared regression line to predict wait time from the number of customers ahead in line, we are typically off by about 200 seconds. The other thing you could be asked about is R squared. R squared is literally R squared. So that number from before, how strong the linear association is, when you square it, you get R squared. Yep. Yes way. R squared is literally R squared. I should really say it's the other way. It's R is actually the square root of R squared. because R squared can be used in nonlinear contexts as well. But in the context of linear association, R is the square root of R squared. And you just have to attach the direction. So put a negative on it, and now it's a negative association. What this does is it describes what percentage of the changes in the response variables are explained, not caused, explained by the least squared regression line with the explanatory variable. So 0% to 100%. You know, I'm going to take that as a compliment. I don't know if it is, Hannah, but I'm hoping that it is. So R squared goes between 0 and 100. 0% obviously means there's no fit at all. 100% means a perfect fit. And all the variation that you would see would be explained by the line. In other words, if all I told you was, oh, there's going to be one more person now, I'm going to see, y'all see me. Y'all understand. This is a good group. Okay, in this case, you have to specifically like, okay, I'm losing myself a little bit here. Come back. R squared, this is the last thing, I promise. R squared is the percentage of variation in the response that is explained by the explanatory. So in this case, it would be the percent of the differences in time that is explained by the number of customers that are in line in front of you when you get in. In our case, it's about 73%. If I take away that one outlier, that R squared is going to go way up, probably much closer to 90-something%. Okay, so in our case, we'd say 73.33% of variation in wait time is explained by using the least squared regression line, using the number of customers in line, and the wait time. You don't have to necessarily say wait time the second time, but it's helpful. Whew. So that's a lot of things. So on here, we've got 100%, Kate. I definitely will. And I'll do a follow-up email from this one with these 4 sentence templates in it, in case you want to just like have them in notes somewhere. Because really the only 4 things that they could ask us about from here is intercept, slope, S, R squared. If I were to rank them in terms of how often they show up, slope shows up the most by far. And then it's kind of tied for second is intercept and R squared. And then a distant last is S. S has been asked about once in the last 20 years in the free response section. So possible, but unlikely. R squared and intercept is once every 5 to 6 years, and slope is like once every 2 years. Slope is pretty common as a free response question. Okay, so with that, I have like one, for the sake of time, I don't want to do a ton with this, but you can see we've got a scenario here. We can ignore that. R squared, don't use the adjusted one, just use the regular one. And I'm sure that you guys could do this, so I'm not going to sweat it. Let's just do a really, really quick one here. Jenny goes for walks on the treadmill, course of 25 walks. She records both the number of minutes she walks and the number of calories burned in the workout. Table above shows the results of a regression analysis in a computer program. So I could ask you to do a whole bunch of stuff here. Let's do a very simple one and just write the equation of the least squared regression line, and then we'll do a recap and get out of here. Let's write the equation of this least squared regression line. Good. Yeah, Hannah, you want to make sure that you would then write a little side thing where X and Y are defined, or put it together all in the same thing, just like this. Expected follow-ups here, I would expect them to then ask you to interpret the slope. They would potentially ask you to interpret either S or R squared, maybe explain why the constant, interpret it, or explain why it doesn't make sense, which it doesn't because she probably never walked for 0 minutes, or something else. One last thing that I will mention is something I could see happening is R squared is a measure of how strong the linear fit is, because it is how much variation is described. Yeah, Allison, I'll definitely do that. one thing that could happen is they might give us like a second follow-up scenario and ask us how R squared would compare in that follow-up scenario. So maybe in a follow-up scenario, Jenny not only does walks on the treadmill, but she does runs on the treadmill and she does yoga or something like that. And then she plots out all the results. In that case, if she's doing different activities, her body might not have the same reactions, and then maybe R squared would be lower because there's more variation. Something like that, where they might try to test your understanding of what R squared represents in context. And if they do, any situation that introduces more variation to the results should probably lower R squared. Is there a chance of confounding variable? Mr. Argo made you run up the stairs? Oh man, that is dedication to something. My class for this, we measured our hand length, and then we reached into a bowl of candy and grabbed as many of the candies as we could. So it was a little mints, like a little, okay, you got cookies. Totally worth it. So that's really good cookies. Okay, well, there you go. So with that, oh my God, what's probability tables? You guys, you guys never did Kung Fu? You guys never did anything with like Skittles or Starburst or any kind of mints or anything like that? That's tough. That's part of the fun of stats. We do, when you get to confidence intervals, you got to do something with proportions. What better way to do that than with candy? That's fun. All right. So with that, this is what we talked about today. I went a little bit longer with the linear regression, but categorical variables, quantitative variables, and then regression in terms of slope, intercept, S, R squared, residuals, reading the computer outputs, describing association. This is where I kind of pause and say, thank you. Appreciate you guys spending a Monday night with me. Lots of puns. It was, I don't want to make more egg jokes. They're a little overdone. They're a little overdone, Yeah. Thank you guys for coming. Next week, okay, we will be getting into Unit 3, and that is experiments and observational studies. So this is where we'll start talking about confounding variables there. That's good to see you guys. I'll follow up with you with an email in the next 24 to 48 hours with some links in here. And we'll do it again next time. And do go over to the community, the Fiveable community tab. I've got a couple of practice problems put up from Unit 2 for you guys to do. Love it, guys. Thank you for being here, and we will do this again next week. I'll stick around for a couple of minutes if anyone has any last-second questions about any of this stuff. Otherwise, take it to the forum, and you guys have a great night as well. Thanks for being here. Bye, Hannah. Thank you. Definitely send some feedback to someone. Let them know. Hype me up. You want to hit up Amanda, let her know. Feel free. But I appreciate that. I try. Thank you. All right, y'all. Take care. See you next week. Thank you, Israel. You are appreciated. You guys have a good one.